Okay, hello everybody. Thank you all for coming. We have quite a lot to get through, so I will go quite quickly. If you like QR codes, you can scan this to view the slides and follow along, but the URL will also be at the bottom of every slide, so don't worry if you miss it. Just a few quick words about me. I'm a maintainer of SciPy and Pixie and Array API Extra and a member of the Consortium for Python Data API Standards, which is what we're talking about today. I'm also a master's student at Oxford studying computer science and philosophy, and I just finished working at prefix.dev on Pixie. Yeah. Just quickly, what we're going through, kind of three sections. First of all, I'll just be giving some context for people who maybe haven't heard about the Array API standard before, just so everybody's kind of on the same page. Then we'll do like a tour of the ecosystem, just going around all of the repos that are relevant and discussing what they're doing. And then we'll also go for a bit of status and what we might see going forwards. Okay. So what we're talking about is arrays. You've probably all used arrays before. They're this n-dimensional grid-like data structure. Probably NumPy is the one you've used the most. They have some restrictions, so they have this like rectangular shape. You don't have columns being different sizes next to each other, and every element in the grid is of the same data type. But these restrictions are nice because it means that it's then very fast and easy to manipulate these data structures. They're used everywhere from the NumPy documentation. Here's a little bit about where they're used in data science and the libraries that build on top of NumPy. Maybe some of you have used this stuff already. Now this is a few years out of date by now, but the point of it is to show that NumPy is not the only array library. In fact, there are lots of other libraries that provide this same data structure. So they might do things very differently to NumPy. They might work on different devices. They might have different execution models, like lazy execution. But fundamentally, they're all providing this same array data structure. And one thing that's helpful is to split this kind of array ecosystem into two parts. We have the provider libraries, which are providing this data structure, and then we have lots of other libraries that are making use of this and using those arrays to do other things. Yeah, as I said, this is a few years old, so we already have a few more libraries that would fill this next array library, next tools column, and we'll get onto that later. But the idea of the talk is that we want to kind of remove these barriers between these like sub-array ecosystems, and what this means in practice is having more of these libraries at the bottom, these array consumer libraries, work with multiple of the array provider libraries and not only work with one of them. Okay, so just a bit more about why we care about this and why we want to do it. One real-world use case would be if you have your software stack, you've written it with one array library, but actually you have some motivation to switch to another array library. This has happened in practice with like reinforcement learning. Maybe you're switching from PyTorch to JAX because in your specific domain it does things that you can do that you can't do with these other libraries. But the interesting part for us is that it's not just that core pipeline that you're going to be shifting across. Because these ecosystems kind of don't work together with each other too well, you'll have to move across all of your other scripts, your I/O, things you might find in SciPy if you're doing some statistics, just some very basic applied maths. You're going to have to kind of rewrite those things and find out how to do them with that new array type. Before this work started, that really wasn't easy. And the goal of this work is, well, one of the goals is to make that nice and easy. Also, we want to avoid repeated transfers between array libraries and devices. This is something that can be quite slow, especially when you're transferring between devices. And it also just increases code complexity. If in your pipeline you're using 3 or 4 different array libraries, it can be difficult to track what's actually going on where. And it'd be really nice if you can just use one throughout your pipeline. Also, just to enable experimentation, you don't need to have a huge established software stack to make use of this. Maybe you just want to try out your GPU that you've got and see how fast your code can run on that, or try out some functionality that maybe only exists with PyTorch, but you've never used PyTorch before, you've only used NumPy. This is useful for you too. Why might these array consuming libraries like SciPy or scikit-learn, why do they care about this? Well, one of the biggest requests that these libraries get is to provide users with hardware acceleration. These libraries that are built on top of NumPy, typically CPU only and eager execution only. And and libraries that are built on top of some of these other array libraries can achieve a lot of acceleration that you can't just building on top of NumPy. And so these libraries are interested for that reason, to be able to access that acceleration. But also they want a way to access this without increasing maintenance burden massively. You, of course, could just kind of duplicate your code 5 times and write it for each array library, but this is not maintainable. It's not sustainable. So we want a solution that can do this without increasing that burden. And also, libraries with useful functionality shouldn't just die. Let's say in 10 years' time, everybody stops using NumPy. I don't think that's going to happen, but let's say for some reason nobody's using a CPU anymore. Then if SciPy only worked with NumPy, then it would just not be used anymore. But that's not ideal. It would be nice if these libraries that don't rely on a specific array library, they just rely on like the concept of an array to be able to keep working in the future, no matter how that array concept kind of exists. Why might array providing libraries be interested in this? So existing libraries like NumPy, it means they get compatibility with new libraries if they're written to support this standard rather than just one library. And also they can make decisions collaboratively with other array library authors. And also new libraries, it gives them kind of a goal. If you're starting up your new library, it can be quite a difficult task to just say, okay, re-implement the entirety of NumPy, but do it on this new device that has come out or something like that. But if you have a specific API with all of the behaviors noted down that you want to achieve, maybe a test suite that helps you with that, then that makes that a lot easier. And finally, just from an ecosystem-wide perspective, why do we care about this? What the situation we have currently is kind of inefficient in this sense, where for each functionality, you maybe have a perfect implementation that does everything you want in one array type, and then for another array type, it maybe just doesn't exist, so you would have to transfer back to a different type, or maybe there's some other implementation that has half the functionality, but it's missing parts you need, and yeah, this is really not ideal. And what we would like for each kind of distinct functionality that you're doing with these arrays, there should just be one implementation that can kind of take in any array type you give it and give it out. This is obviously slightly idealized, but this is the general concept that we're going for. Okay, so how are we actually going about doing this? It's a quick diagram that might help you understand. The process starts in the center of this diagram, where we have a common API, which these array libraries like NumPy, like PyTorch, like whatever other array library kind of agree, okay, we are all going to provide a function called mean. We're all going to provide this way of creating an array. We're all going to have this specific behavior for this function. And what that means is that in this second ring, libraries like SciPy, scikit-learn, these kind of core consuming libraries, can write to this API, and it will work with all of these libraries that adopt it. It's not, they don't have to do like if-else branches all over the place to accommodate for differences in the API. They can just use this one API, and it will work. And then finally, on the outer ring, we have kind of any other array consuming library. There are lots of libraries that maybe have lots of dependencies. Maybe they just depend on SciPy, just depend on scikit-learn, things like this. They kind of need these core libraries to adopt it first so that their dependencies have this. But then once this has happened, they can start adopting it as well. And yeah, we'll see a bit later that that has already started. And who is actually working on this? This is the Consortium for Python Data API Standards. So it's a cross-ecosystem consortium with stakeholders from lots of different array libraries and also consuming libraries. And yeah, it's been working on this for about 5 years now. Okay, on to the tour. We're going to go through these different libraries. These are all libraries under the Data APIs organization on GitHub, and just talk about what they do. First of all, the array API standard. So it's actually not just an API specification. It has lots of other pages that you can find on the website that talk through kind of design choices, assumptions that are being made, why this is a good idea. But the part maybe we're most interested in is this API specification that contains kind of all of these functions that we're saying, okay, you need to have these things if you're going to count as an array or an array library. And yeah, for each function, tells you what are the parameters, what behavior should it follow, what should it give you. And yeah, this tells the array providing libraries what they need to implement, tells the consuming libraries what they can use. So SciPy, when we're writing new code, we don't need to check all of these different array libraries and see how do we do this thing. We just check the standard and use what the standard says. Now, yeah, there's a lot more to say on the standard itself, but that's already been covered quite well in this talk from SciPy 2023. So if you want to hear more about kind of past work, design principles, methodology, then go and give that a watch. We also have array API tests. Now, this is a test for compliance with the API. So this is for these array providing libraries like PyTorch, like NumPy, like CuPy. They can run these tests in their CI. So every time they make changes, they can check, is this compatible with the specification, or is this actually breaking something? Or if you're a new library, as when you're first starting, you'll get a whole bunch of failures saying, this is why you're not compliant, this is why you're not an array library yet, and they kind of have a checklist to work through. We also have array API compat. Now, this is a compatibility layer for existing libraries. So, of course, these libraries are not instantly going to adopt this API straight away. So this contains wrappers for those libraries. Some, like NumPy, have adopted this API pretty much perfectly into their main namespaces now. So the wrappers are actually quite thin. Some of them, for larger, more established libraries that are slightly more difficult to change, have some larger wrappers like PyTorch. But yeah, so when consuming libraries are adopting this API, like SciPy, like scikit-learn, they're actually going to be getting these namespaces from array API compat from their arrays. And that means that when they're calling these functions, they will go via this compatibility layer, and that can handle any like name changes, any extra like small behavior things that need to change. But it's not just these wrapper namespaces. It also has helper functions. The most interesting one is array namespace, and this shows you how this actually works when you're adopting it. So this is a real implementation of the whiten function from SciPy right now. And the idea is that whenever you get an array as an input to your function, we're going to call this array namespace and save that as XP. So this is just like NP for NumPy, but it represents just any array library. And then down below in the function, we're going to use functions from that. So like when we would have been using np.standard for the standard deviation before, we're now using it from XP. And yeah, there's a few more things here that might look a bit questionable, but yeah, we'll get onto them. Okay, next library, array API strict. This is a strict minimal implementation of the standard. This is, again, something that's going to be helpful for consuming library developers. And the idea is that if you run this through your test suite, it should catch if you're relying on any unspecified behavior. So maybe NumPy has some functions in it, and maybe PyTorch has those functions, and all of these libraries have these functions, but they're not actually in the standard. If we were only testing with those array libraries, then maybe our tests wouldn't fail. But then if some new library comes along and adopts the standard, then suddenly it might break if the functions we're using aren't standardized. So testing against array API strict is helpful because it means that we're going to find that out straight away. And how do we actually change our tests? If you're using PyTest, it's quite easy. You can just parameterize your existing tests with an extra XP. And then whenever you are using, let's say, NP, or if you're using a different library in your tests, you will just construct these XP arrays, pass them as input, and then test with the output that they're giving you back the XP arrays that you want. And I'll say a bit more about this XP assert close soon. Next library is Array API Extra. This is another library for consuming library developers. And it has a few things in. Firstly, it has some extra functions built on top of the standard. And these are functions which are typically widely useful. It wouldn't make sense to just put them in one consuming library like SciPy or scikit-learn. Maybe lots and lots of consuming libraries are going to need this and wouldn't want to depend on those libraries. But these are things that are often easy to implement in terms of the standard. So it maybe doesn't make sense to include them in the standard if they can be implemented in kind of 2 lines anyway. Also, maybe they're just not widely adopted enough to go into the standard yet. but we can have an implementation that's in terms of the standard and can work with all of these libraries. It also includes delegation to existing implementations. So if an array library does want to offer a particularly fast implementation for one of these functions, then we can still use that. So that's what the API reference looks like. Some things like isClose, Kronecker product. These are things that are maybe a little bit too niche or maybe just not widely adopted enough to go into the standard itself, but we can implement them. Secondly, it also has some tools for lazy backends. So some parts of the standard are like optional to implement because they're quite difficult to implement for libraries with lazy execution models. And also libraries with read-only arrays can hit some problems. But we have some workarounds in Array API Extra to make this nice and easy. One thing is for like in-place modifications of arrays. We have this xpx.at function. And this is basically doing this like in-place modification, but making it a functional style. And this means that it can work with lazy backends. Just for comparison, we have a Python implementation of how this would work for NumPy arrays. And this is the behavior that's exactly equivalent here. We also have things like lazy apply to lazily apply an eager function. So if a function has to be eager, we might still want to kind of embed it in this lazy framework rather than it just throwing us an error. And this can help with that. And thirdly, it has some testing utilities. So we have this xpx.testing namespace, which helps. Right now, it's helping you with lazy libraries. How do we test JAX under JIT? How do we test Dask? How often is it materializing the arrays it has? Again, we can use that with the XP fixture, just like we used with the testing array API strict. But hopefully we're going to get some more things in here in the future, like that XP assert close function that I showed earlier. These are kind of things from np.testing, which you might use a lot if you're testing your NumPy library, just to check that the actual array you got from your function is the one you expect. We would like to implement kind of array-agnostic versions of these, which work with any array library. And yeah, hopefully that's coming soon. Final library here, we have Array API typing. There's also experimental static typing support in the works for the standard. Still quite early in development. Yeah, it's not quite ready to be used by consumer libraries. But if you want to adopt this, but you have the restriction, oh, everything in my library is really nice and typed, I'm going to need that, then yeah, this is also hopefully coming soon. OK, so that was the whistle-stop tour. Now a bit of status, kind of where are we, where might we be going in the future. In terms of array libraries themselves, ones you might have heard of, NumPy, CuPy, jax.numpy, these have pretty much full compatibility in the main namespaces, so you could almost get away without using Array API compat with these for now. PyTorch has this compatibility via Array API compat. Dask.array also has it. Some caveats with Dask of things that are missing, but it has most of it. And we also have lots of new libraries that maybe you haven't heard of yet. NDONNX, we have Cubed, which is like similar to Dask, PyData sparse for sparse arrays, also BLOSK for compressed arrays. And yeah, we have some more libraries here, like Paddle and MLX, who have not started implementing the standard yet, but they have been interested. In terms of adoption in consuming libraries, SciPy, I'll talk about that first, since I'm a SciPy maintainer. How users actually enable this is by setting an experimental environment variable called SciPy Array API. If you don't set this, then nothing changes. Everything will just be the old behavior, which assumes you're giving NumPy arrays. And if you give something else, who knows what will happen. But with this variable set, then it will use this Array API compat infrastructure, and it should be able to handle whichever array you throw at it if it implements the spec. We also vendor Array API compat and Array API extra now, just to have it nice and stable, but you can also depend on these just via PyPI or via CondaForge. We're testing right now against Array API strict, CuPy, Torch, jax.numpy, Dask.array. We're doing this in CI. We're doing CI runs with GPU jobs. If you wanted to start adopting this, you wouldn't necessarily have to do all that. Just testing against Array API strict is a nice start. But for a big library like SciPy, which has lots of people depending on it, it's really nice to be able to exercise all of these different libraries and make sure that they're all working. Also, quick shout out, we're using Pixie for reproducibility in these jobs, and that's been really nice with GPU jobs especially to get those working nice and easily. We also have some nice documentation now with API coverage tables. So if you're depending on SciPy, but you're not sure if we've covered yet what you need, you can check this documentation. So per module, you can see, is there support for CPU arrays? Is there support for GPU arrays? Maybe you're using JAX. Is there support with the JIT? And you can see down to the function level which of these are there. And tell us if there's stuff that you need that we've not done yet, and we can see. Or contribute. But quick caveat, we've mainly been talking about Python. This array API standard is at the Python level. It helps if how you're calling these array libraries is at the Python level. Actually, SciPy is often interacting with NumPy, not via Python, but via C. And yeah, we have lots of other languages that are not just Python in SciPy. So we do kind of need some different approaches here. One thing is to just do if-else and kind of go back to this delegation of, OK, maybe CuPy does implement a different version that we're using C to call NumPy here. Well, we can just say, if it's CuPy, go over there. Otherwise, we'll use our C implementation for NumPy. That kind of works if these existing implementations exist, but it doesn't scale well. And if you've got a niche library that nobody's ever implemented for CuPy, then you'd have to do that yourself. So yeah, that's not the ideal solution, but it's an option that we are using in SciPy to help enable this acceleration right now. Some work maybe for the future is on dispatching, which is kind of making this delegation happen automatically. So when you give it an array, it will automatically kind of find out what is your array type, and you can maybe register backends. So you could install maybe from PyPI a GPU backend for this part of SciPy and register that, and then that would get used automatically. This is still in the works, but yeah, it's hopefully coming soon. A final option is to just rewrite these things that maybe exist in C or in Python for NumPy in Python, and then use the array API standard there. So we've done this for scipy.spatial.transform. There are now 2 implementations living in SciPy. We have this array-agnostic version in Python, which works with all these libraries. And then we have a Python version for NumPy that's a bit faster just for NumPy so that we don't have this performance regression, but we can still support these other libraries. Kind of not ideal because you have 2 implementations, but we deemed that it was worth it because you then get all of this acceleration and access to other libraries. And some benchmarks, we can see the kind of orders of magnitude speeds up here for very large arrays, especially when using JAX, especially when using the GPU. Scikit-learn is a very similar story to SciPy, also using this same environment variable, also vendoring these libraries. Update from Olivier, it has 3,800 plus tests. Again, like SciPy, lots of different devices, different D types being tested here. If you use scikit-learn, this probably means a lot to you. It has estimators and yeah, lots of public functions being covered. Yeah. It also has documentation. So you can see at this table, again, if you need to check the things that you depend on covered, you can check that. It's not just SciPy and scikit-learn. There are lots of other libraries that have also started adoption. These are some libraries that are on the outer ring, maybe, of the diagram I showed earlier, that are maybe depending on SciPy, and now they've got the parts that they need covered, and they're starting to adopt the standard as well. We also have some quick bonus projects to mention. These are kind of blurring the line between what is an array library and what isn't. marray, what it does is it wraps any array library that you give it. So you can give it NumPy, give it PyTorch, and it will give you that array library back, but add on the capability for masked arrays. Some of you might have used masked arrays before. They're in the numpy.ma namespace. They basically help you when you have missing data and you want to kind of put a mask over your data to say, OK, whatever data's in this range, ignore that. That was missing. Or my input device was having some complications there. Let's just ignore that data. You can do that nicely. I've also got a little prototype for units with any array library backend here as well. This is, again, something that's very early in development, but if you use units, then this will be interesting for you as well. OK, looking forwards, what's coming next? Main thing is just more adoption in consuming libraries. We're still under heavy development in SciPy and scikit-learn, trying to like complete this coverage of these libraries, or at least everything that people are wanting to use. We're also wanting to upstream some testing utilities, like I mentioned earlier, these assertions that you might find in numpy.testing to Array API Extra. SciPy and scikit-learn have some solutions for this already. We just need to figure out what's the best way to do this in a standard way that then everyone can use. And yeah, like I mentioned earlier, also Array API typing, getting that static typing support up. We have a sprint, which is on Thursday, if I remember correctly. Yeah, you can come and chat about the standard. You can also contribute to this coverage in scikit-learn. There's quite a few scikit-learn maintainers here. I'll be here briefly as well if you want to contribute to Array API Extra or chat about something and then contribute online. That also works well. Yeah, just final thanks. Thanks to all of the contributors to the projects discussed in this talk. Wouldn't have been possible otherwise. Also, Ralph Gomez for leadership of the consortium. He has a keynote this afternoon as well, which will maybe be putting this work into context, into a bit of the bigger picture, so definitely go to that. Also, Patrick Roddy for this talk template that I used, the PyData Paris organizers and volunteers, and yeah, everyone for your attention. Thank you.
Do we have maybe one quick question?
Thanks for the talk. I had a question. So as it pertains to this, the Array API, I'm guessing it deals with in-memory operations, but does it also define any standards around loading arrays from like storage, and as well as saving that back to like some storage format?
It doesn't have kind of loading from storage or saving to storage specifically. It does have the data interchange protocol is DLPack, which is about how you can kind of get these capsules that you pass arrays around between these frameworks. To be honest, I'm not sure exactly how that interacts with saving these things to out-of-core storage, but yeah.
So maybe let's move on to the next talk. If you have any more questions, maybe later, because otherwise we started a bit late. So thanks, speaker again.